Hello, we're Team M, presenting Lola's 2.0. Just a reminder, I'm joined with Daniel, Jaden, and Eliza, and our main client is UNC nutrition professor Lindsay Smith-Daly. But our main points of context throughout this project have been postgrad Kayla Connors and undergrad research assistant Jeremy Wang. As an overview for today's presentation, we'll be going over a platform reminder, a demo of our actual product, a description of our final architecture, a little deeper dive on the back end, as well as discussion on the lessons learned. So to start, I have the platform reminder. We were creating an over-the-shoulder dietitian that provides healthy, on-demand recommendations while shopping for groceries. And the way we actually implemented this was a web extension that when a user opens a product page on walmart.com, the extension will capture the product information, send it to a backend, and then return to the user a healthier alternative, with the idea that this would mimic a dietitian that is, for the most part, unobtrusive. It just sees what you're looking at, and then gives you recommendations based on that. For the platforms involved, we had a script, a front end, and a back end. The script was just a Python script that would scrape information on Walmart.com that we later load into our database on the back end. The front end is an extension that's loaded into Google Chrome. That's the only environment that we've worked in, but in theory, it should work with other Chromium browsers. And then for the back end, we did a locally hosted fast API, which connects to a locally hosted Quadrant database. And then finally, we developed within a Docker virtual environment just to keep it consistent. And all of these were coded in VS Code.
And I'm going to give a short demonstration of our front end, which is a browser extension named Lola's 2.0, and we can see that it's loaded right here in our extension manager. So if I go to Walmart, then I can look for a product, and the idea is that the user is somebody who's had trouble with their diet. So as soon as they click on a product, our web extension will embed a recommendation directly into the HTML of the page with with a healthier option, and they can click this link to view the product. In the case that their HTML doesn't match our expected version, there is a fallback as well. They can click on the browser extension, click this button, and they will see the recommendation right there. This link works as well. And we made this fallback, A, just for preference. Some people might prefer that view, but B, the main reason is because in order to embed into the Walmart webpage, we had to search for a specific element ID, and from what we could find, just based on trial and error as well as research, the add to cart button tends to be given the same ID. So hopefully this will work for all users, but in the case that that ID is not found, nothing will be inserted into the HTML, and so the user will have to revert to using that. But yeah, we can look for another product as well. And yeah, Coca-Cola. And it recommends them Fresca Citrus Soda Pop. So much better. They can click the view product link there and this product link as well, redirected in Walmart.
Moving on to the architecture, I wanted to start by looking at our deal system architecture from the start of the semester. While we accomplished a lot of this, some things that we did not get to would be the cron job for the web scraping. The grocery store list, we did only do Walmart, so we did not make it to the other ones. In terms of the database, we have Quadrant, but we did not get the Postgres database. And then for the extension, a lot of the actual processing was moved to the back end, and it wasn't quite as complicated as we have it here. So here is the actual final architecture of our product. You'll see that the green on top corresponds to stuff working with the script, and then the purple on the bottom corresponds with the actual web extension backend. So just go over the bottom portion quickly first. A user will open a product page. The web extension Google Chrome will go to Walmart. The web extension will pull the product information. That information will be sent to the backend, our fast API server, where it'll do a similarity search to quadrant to get so tunable number of similar items. The backend will process all those items, decide which of those is the healthiest, return that to the web extension. The web extension will display the output to the user. Then for the actual script, one of our team members will input a list of search queries. The script will scrape Walmart, searching those queries. It'll pull the product information as well as all the images associated with each product. Those images are then sent to a local OCR. This will give us the text from the images. The script will decide which of those images, since we now know the text, correspond with nutrition information. Those will get sent to Claude. Claude will give us the nutrition facts, and then we'll get a clean JSON for the user. The user, one of our team members, will then take that JSON and be able to upload it to the database.
Hi, this is Daniel, and Jay and I will be presenting our backend of Lola's 2.0. Our backend consists of 3 components: our API, service layer, and database. The API is designed to support fast, scalable, machine learning-driven product retrieval and recommendation. We use Fast API as our framework of choice because it gives us clean routing, built-in request validation through Pydantic, and automatic interactive documentation via Swagger UI. At this stage, our primary fully implemented endpoint is /quadrant. This post endpoint uses Fast API's dependency injection system to provide an instance of quadrant service, which encapsulates all of our vector search logic. When a request is received, we call the service's query and recommend method, which obtains a set of product recommendations ranked according to the specified criteria. The API serves as the backbone for the Lola's 2.0 browser extension, powering its core functionality. All product recommendations, nutrition insights, and metadata displayed in the extension are retrieved through this API, enabling a seamless, real-time user experience. On this slide, you can see our product request data type. This represents the input a user sends to the /quadrant endpoint when requesting recommendations. It captures the essential information needed to embed, compare, and retrieve similar products from the vector database, including fields like product name, description, and price. We present our product return data type. This defines the structure of data used to generate recommendations and display them on our front-end extension. It includes key details such as the product name, price, and other relevant metadata. Embedded within it is the nutrition facts data type, which encapsulates nutritional information for each product. This information allows us to calculate a health score, ensuring that recommended products align with both similarity and nutritional considerations.
Hi everyone, Jaden here. Now I'm going to go ahead and talk about our service layer. So this covers the recommendation algorithm and basically explains how we get items from our database, how we sort the items, and essentially recommend the healthiest alternatives possible based on whatever item the user is looking at on the front end. So we have this quadrant service class. This allows us to better organize our code. Next, we have this query and recommend function, which generates a query based off the item that the user is looking at. So we take the name of the product and also the product description from the item the user is looking at. We turn this into a vector using this embed function, and we perform the similarity query, and we get 20 items. That's just what limit is specified as, but you can obviously change this to whatever you want to either broaden or make your searches more specific items. Next, we create these rankings. So we have fat, sodium, and sugar. These were the nutrients specified by our client that we should focus on when generating a health score. We take the average of all 3 and then generate a composite score per item. And then lastly, we take the top 5 items of those 20 after the composite scores have been applied. And then we return on the front end the absolute best possible alternative to the item the user is looking at.
For our final iteration, we did not change much about how we query quadrant, but we did abstract all of our scoring logic into scoring service, which is a class that is injected as a dependency into the quadrant service upon initialization. After we've obtained our data from the database, we fit them all to the aforementioned product Pydantic model, and then pass them into our scoring services obtain recommendations function, along with the price of the original product. The scoring service is designed to rank products based on multiple criteria, primarily focusing on healthiness, ultra-processing, and price proximity. These criteria were provided to us by Dr. Connors of the Nutrition Department, our client, and leverages added sugar, sodium, and saturated fats to compute a health score and then combine it with other heuristics in the waste class to return a ranked list of product recommendations. The class is structured in a modular way to make the scoring logic clear and extensible. The landing function of the service is our obtain recommendations function. It returns a ranked list of products based on 3 criteria: health score, an ultra-processed flag, and price proximity flag. To calculate the health score, it calls the health score method, which evaluates the health score of each product by taking the mean percentage of harmful nutrients, our saturated fats, added sugars, and sodium, and subtracting this value from a defined maximum score. 2 helper functions support this process: obtain DV, which organizes the daily value percentages for each nutrient, and extract DV, which extracts numeric daily value from the product's nutrition information. In the future, when serving size is more consistently available in the data, the extract serving size method will identify the product serving size. This will allow the standardized DV method to convert nutrient daily value percentages into a standardized per 100 grams/milliliters format, making health scores more accurate and comparable across products. Overall, the structure of our service layer ensures that recommendations are both health conscious and aligned with user price preferences. It focuses on modularity to assure that the algorithm can be more easily iterated upon and scaled in the future.
Now let's circle back to the database component of the backend. So why did we use Quadrant in the first place? Well, Quadrant allows for a very unique type of querying and searching from the database. So it allows you to perform this thing called semantic search, which enables you to look at the meaning of each field or just the payload as a whole. But specifically, we look at the meaning of the product name and the description. We decided with Quadrant's compatibility with LLMs and its ability to also perform BM25 information retrieval or keyword search, Quadrant makes a great addition to our project with the idea in mind that our client is probably going to integrate their own LLM with our project in the future. All right, next I'm going to talk about how we created and curated the database. So we define this function called extract upsert, which essentially allows you to take any JSON file, parse through it, and then upload however many items you want from that JSON file into the database. So in this scripting chunk right here, we use the with open convention to open the JSON file, and then we parse it, looking for all of the specific fields that we need. We fill up a payload object, and then we put the payload into our payloads list. Next, we use the embedding model to embed all of the specified documents from our JSON file that we extracted from our previous step. We put it into our Quadrant database using this .upsert API function from Quadrant, and then we index them using this ID convention. All right, so now I'm gonna kind of dive into how semantic search works behind the hood, because if you saw earlier in our code, there wasn't any like NumPy or math functions because it's all abstracted behind Quadrant's APIs. So we decided to use a text embedding model called FastEmbed. It's because it's reliable, lightweight, and it's also free, and this works pretty well with production level projects. Next, for the semantic comparison method, we used cosine angle similarity. So this specifically measures the direction, and this is very useful for performing high dimension comparisons and recommendations. So specifically because our project was a recommendation service, we decided to use cosine angle similarity. I'll also dive into a couple alternatives. So we have Euclidean, which is a magnitude-based similarity function. This allows you to basically see if certain keywords are showing up a lot, but this is better for low dimension similarity. Next, we have Manhattan. This is useful for clustering algorithms. Here's a kind of a demonstration for how cosine similarity works. So if you have hi world and hello world, it creates an angle between the two vectors in multi-dimensional space. This is just R3 space, but we decided to use way more dimensions than that. And say they were the same word, you would have the same dot product. The dot product would be equal to the magnitude times the magnitude, which would just be 1. And if they have an angle of, if the cosine is 1, that would be the score, and that would be the highest recommendation possible. And so the values just vary between 0 and 1. And yeah, that's semantic search for you guys. As for a couple of lessons learned, we wish that we implemented Docker and a virtual environment for the scraping script in the front end earlier in the process, as this would have helped us ensure consistency throughout all of our dependencies. Additionally, we wish that we focused more on GitHub cleanliness and ensuring that we use proper PRs for the main code to ensure that all changes were communicated throughout our entire team. This would have helped a lot with resolving merge conflicts and just avoiding them all entirely. And lastly, just making sure that our code was organized into classes. This helped a lot with debugging later on.